Hello everyone, welcome to today's class. In this lecture, we'll start with linear programming. Now, the kind of problems that you usually have in these linear programming, they are based on optimizations. If we look at a practical situation, let's read this condition. The problem states that there is a furniture dealer who right now dealing with only two items. He is selling tables and chairs. Okay. He has rupees 50,000 to invest. So that's the upper cap, that maximum he can invest is 50,000, and has storage of at most 60 pieces. Means the total number of chairs and the tables that he can store in the storage space is 60. Okay. So that's a restriction on his part. Now the table cost 2,500, chair cost 500. All right. He estimates that from sale of one table he can make a profit. On table he can make a profit of 250. On the chair he can make a profit of 75. So find the number of chair and table for maximum profit. Now this is a perfect example of linear programming where right now you have two variables. Okay, one is the table, how many tables he has to sell out or he has to buy it to get the maximum profit, and how many chairs he has to buy. But it is subjected to some restrictions that we call as constraint. Okay, the constraints are that the total amount he has to invest is 50,000 and he can have total number of chairs and tables as 60. Okay, that's your main problem, the optimization problem, and linear programming helps us to solve this situation because we cannot assume, let's take some random number of chairs and tables and put down the values to see what is the profit coming out to be, is it maximum or not. Okay, let's see what is now the definition of the optimization problem, and then we'll create the equations for this, convert this language into mathematics and how to solve it. So a problem which seeks to maximize or minimize, first of all it deals with both the parts. It can maximize also, it can minimize. If we are talking about profit, of course we want to maximize it. If we are talking about losses, of course we have to cut it down. So, or if it is the cost, that is the parameter that needs to be minimized, so that needs to be minimized effectively. No? Is a linear function. Now linear function, that is very important, means there cannot be having a dependency with the power of 2 or 3. I'll tell you when I create the equation what is the effective meaning of linear. But right now we will again say two variables. As such we can do it for more variables also, but then it becomes more complicated. So as per the syllabus part is concerned, we'll be dealing with only two variables, x and y. Okay, and they are subject to certain constraints, like the constraint we had in this question, determined by a set of linear inequalities. Okay, so the conditions are also linear as such. Okay, they are called optimization problem, and linear programming are a special type of optimization problem. This is a very specific type of optimization problem. I mean, there can be more variety in this, but these kinds of problem in which we are dealing with linear variables as such, linear conditions, linear inequalities, that consist of our linear programming problems. Let's convert this language into mathematics now. So first of all, let's take number of chairs and number of tables also. Let number of tables, they are x. Let number of chairs that he bought were y. Okay. Now since x and y represents number of things, the number of things cannot be negative, so automatically a condition is implied, that is x should be greater than 0 and y should also be greater than equal to 0. Okay, they are also called non-negative constraints because number of things cannot be negative. It can be 0, means you don't buy any chair, you sell only tables, or you sell only chairs, but you cannot have negative number of tables or chairs. That doesn't physically imply anything. Okay, let's talk about the constraint effectively. uh, the maximum storage was 60 pieces. That means number of chairs plus number of tables, okay, x plus y, should be definitely less than equal to 60. Okay, so that is one constraint. Second constraint was, or second restriction was, that the total amount has to be 50,000. He has maximum he can invest is 50,000. That means that doesn't imply that he has to exactly amount it to 50,000. He can spend lesser than that also, but that is the upper cap. Okay, so one table is costing him 2,500, so 2,500x, and one chair is costing him 500, so 500y. So that should be your total cost of your investment basically. So that investment has to be less than, again, 50,000. It cannot be beyond that because the question specifies that. Now these were non-negative constraints, they were automatically implied. Now these are the constraints. Okay, constraints or conditions as per the question. Then the question is about making profit now. So let's talk about profit. So on a table he can make 250 profit. So 250 for x number of tables, he'll have 250x profit. On a single chair he has 75 profit. So on y number of chairs, 75y. That is the profit that we will represent as z, some other variable as such. We can call it another, apart from that we can name it anything else, but most of the time in the question also you'll get z. Z will be your main function that you need to maximize or minimize. Okay, so this needs to be maximize. Okay. Z is also called objective function. So the names I'm giving you just for reference. They may ask you, in some MCQs. So any linear function z is equal to ax plus by, where a and b are constants, some other constant. Right now a and b are 250 and 75. Okay, which is to be maximized or minimized is called linear objective function. Again, linear. Now why? Oh, I didn't explain the linear part. Now why I was emphasizing on that, because if you look at the power of x and y, in the constraint also the power of x and y are 1. Okay, and in the profit also the maximization or the optimization objective function, that is also again in the power of 1. That's why we are calling as a linear, because if you remember grade 9th basics, linear means the degree or the power, basically highest power, equal to 1. Okay. Nobody is going to ask you, but just for your reference, why they were called linear, because the highest power of the variable are 1. Okay, so the moment it becomes 2, 2.5, 3 or any random number, it is not a problem of linear programming. It is an optimization problem, but it's not a linear programming now. And remember, the objective function is always in this format, ax plus by. Okay, x and y, they are also called decision variables. Okay, because they are deciding the value of x and y. They are deciding what will be the maximum value of your profit or loss, or minimum value of the loss effectively, or cost. Okay. Constraints are linear inequalities like this. These are the linear inequalities. Okay, or equations or constraints, restrictions, whatever you want to call them, on the variables, they are called constraints effectively. I wrote that they are called constraints. And the condition x greater than y, x greater than 0, y greater than 0 are called non-negative constraint. Actually it is slightly wrong here. It is x greater than equal to 0, y greater than equal to 0. They are called non-negative constraints. Okay. All right, now let's learn how to solve this. Okay, For that, I'll take these equations again. All right, in order to solve this, we need graph. Now, because we are dealing with inequalities, if you can recall, linear inequalities, they are drawn on graph and they are solved based on the common region. If something you can recall from linear inequalities. Okay. Okay. 1 second. It's not working. I'll rewrite this. I don't know why it is not working. So the first constraint was x plus y is less than equal to 60. I think we wrote equal to or not? Equal to. Okay. Second constraint was 250x plus what was it? 500y. 500y. So it must be 2500, huh? 2500, sorry, my bad. 2500x plus this less than equal to 50,000. Of course, practically you can see this. You can take 500 common from this equation, so we can further modify this equation. Let's modify this equation. If we take 500 common, so this becomes 50x plus y less than equal to 500. If 50,000, that will cancel it. So if we cancel this, we'll get 100. All right, fine. Now I'll rewrite this equation again. Second equation, instead of this, we'll write 50x plus 50x is 5x, I think. Sorry, 5x plus y is less than equal to 100. All right, let's remove this equation effectively. We need a space effective. Now, if you can recall from linear inequalities, how do we draw this linear inequality on graph? It will be much simpler. Those who cannot recall, go through those lectures. I'll try to explain on a slightly quicker manner here. Okay. First of all, consider this equation actually x plus y equal to 60. Forget about the inequality. Now get the 2 points, at least 2 points, x and y, through which this straight line passes. How do we do that? We put value of x as 0, we get y as 60. We put value of y as 0, we get value of x as 60. So this is like from grade 10th. How do we plot the straight line? So if I take the points like this, equal gap, 10, 20, 30, 40, 50, 60. Okay. 10, 20, 30, 40, 50, 60. Okay. So I got 1 point as, this is 1 point, 0, 60. This is the second point, 60, 0. Okay. This is 0, 60, 10, 20, 30, 40, 50, 60. Here. Okay. This is also 60. This is 0, 60. 60, 0. If we join these two lines, these 2 points, I mean, we get ourselves a straight line, but that's not the end part of it. Okay. X-axis, y-axis. Now, to get the inequality part, what do? We rewrite the condition x plus y less than equal to 0, and we take a test point. Now the test point can be any random point, and most of the time we take test point as origin. Okay, that means you put the value of x as 0, you put the value of y as 0, and check if the condition is true or false. 0 plus 0 is less than 60, true. It is true. What does that imply? See, this line is dividing the whole XY plane in two parts. One part above the line, one part below. Now we will select that part which contains the origin. Why? Because we chose our test point 0, 0 and the condition is coming out to be true. That means out of these two shading areas, we'll select the one which contains the origin. And what do we say it like? Usually we say it will shade towards the origin. Okay, so true, that means we will do the shading towards the origin. If it was supposed to be suppose it comes out to be false, then we would have shaded the area away from the origin. Okay, so right now the shading is, I'll mark with the arrow rather than completely shading it, like that we have to shade below this line, okay, towards the bottom of this. Now for the second equation, I have 5x plus y that is less than or equal to 100. So forget about the inequality, let's take equality and get the points. X, y. If you put x as 0, you get y as 100. Okay. And if you put y as 0, you get x as 20. So 10, 20, 20 is here, easy. Okay, 10, 20. I can mark it. 10, 20, 30, 40, 50, and that was 60. 100 for that, I'll have to now extend this line. This is one big problem in the exam also, that you either need a proper graph with this, or if you are doing with the pen and pencil directly, so you need an approximated graph. Okay, I'm not using any scale, so you can see I'm doing it freehand. 60, 70, 80, 90, and I need 100. Okay, 0, 100. So I'll draw this one. This one we drew with red color. This one will draw with green color. Okay, so we'll follow this idea for every single line. The first line will draw with red, and second one will always draw with green. All right. Zero, 100. Roughly like that. All right. Now, same thing we have to do again here. We need to decide whether the shading will be towards the origin or away. So let's write down the linear equality. 5x plus y, again less than or equal to 100. You put the test point as 0, 0 always. Put x as 0, y as 0. So 0 plus 0 less than or equal to 100. Again it is coming out to be true. 0 is less than 100. True. That means again we will shade towards the origin. Towards origin. Okay. So we are going to shade towards the origin for this line also. Now see, why did I properly shade this? Because you need to effectively combine all the constraints together. That means you have to give a common region. I think there were non-negative constraints also involved. We didn't wrote them, but we had other constraint also. Let's say the third condition was x should be greater than or equal to 0, y should also be greater than or equal to 0. What does that imply? X greater than 0, y greater than 0. Isn't this the first quadrant? That means we have restricted ourselves to the first quadrant. That means all the shading that is going to happen will be in the first quadrant only. Okay. So it has to be in the first quadrant. It has to be below this red line and below this green line. Both should be done. So below this red like this, below the green again like this, towards the origin, but we cannot cross the quadrant. So if you look at this part, this is the common region. Okay. This is the common region for all the constraints. We have followed all the constraints, the two constraints that were given in the question, the non-negative constraint that were automatically implied. Okay, this particular region, this is what you call as feasible region. Okay. Feasible region, and all points inside this. So in a particular region, you have infinite number of points, of course, inside this region are called feasible solution. So how can we check now? We cannot check infinite amount of points. Of course, the graph has helped us to restrict the condition so that we have to select the points in this region, but we cannot again check for all the points. So what we can do is use the theorem of LPP, which says that the maxima and minima will occur on the corner points. Now, what are those corner points? Look at this. I'm calling this as A, B, C, D. A, B, C, D, they are the corner points of the feasible region, and the theorem says that, as per the LPP theorem, that the maxima or the minima will always occur at these corner points. That means we don't have to check for infinite points. All we care about is these 4 corner points. Okay. So those points A, B, C, D, they are called corner points. So let's write down corner points. So we have A, B, C, D. A is simple, clearly from the graph it is 0, 0. B is 20, 0. Okay. C we don't know as such here. And sorry. D is 0, 60. All right. Now what we need to do is, first of all, we need to get the C point. I'll tell you how to get the C point, but point is we need to create a table, corner points, and the Z function. Z function was the maximize, the condition that needs to maximize the profit, which was 250x plus 75y. So 250x plus 75y. We need to maximize this. So that means we'll calculate the value of Z at these points. Okay. Now comes the very crucial, very important part as such, how to get C point. If we had a proper graph, this was done, we can calculate C point with the help of graph directly. Okay. But if we don't have the point C, then how can we calculate? Okay. So to get C point, we have to go through the concept of linear equation from grade 10th. The concept states that if you have two linear equations, the point of intersection C is the point of intersection of red line and green line. The point of intersection is the solution of the two equations. That means the two equations which were x plus y is 60 and 5x plus y equal to 100. If we solve these two equations, the solution of that equation will be actually this point on the graph. So to get this, we have to solve x plus y equal to 60, 5x plus y equal to 100. If we solve this equation, so let's subtract these equations, y cancel, minus 4x equal to minus 40. So x is coming out to be, cancel, x is coming out to be 10. You put in the y in any of these equations, you get the value of y as 50. Okay. We got the, we can pretty much assume it also, like it is very getting close like this. But see, you cannot be always sure because you have drawn this freehand, so you can always have error. Okay. So to avoid this, I will always recommend to solve the equations to get the corner C point. Okay. So now we got this point. The point is 10, 50. So we got the C point also. Just because we worked slightly hard to get the C point doesn't mean that the maxima or minima will occur at this point only. It may or it may not. Okay. So remember that it's not necessary that since we are solving to get this point, that means it has to be maximize the risk. Sometimes it happens and sometimes it doesn't. So don't be so sure of it that always the intersection of the 2 points will be the condition for the maximum or minimum. No, not like this. Okay. Let's calculate the value of z at 0, 0. If we put x as 0, y as 0, the value is coming out to be 0. If we put x as 20, so 20 into 5, 250 into 20, that gives us 5000. Okay. 10, 50. So 250 into 10 plus 75 into 50. So that's 2500. 75 into 5. We got 5 to 7, 37. 37 and we got 6250. So I'm erasing this now. 6250. Of course, right now this is the maximum we're getting. And if we put 60, so 75 into 6, 30, 42, 45. That is even less than 5000. So clearly, this is the winner. This is the maxima. This is the maximum value we are getting. So profit is maximized at x equal to 10, y is equal to 50. That means that the point that we solved, okay, was the point of maximum. But again, I'm telling you, it's not the always directly this solution. Okay, sometimes what will happen, even after solving this, you will not get the maximum value at this. Somehow you'll be getting maybe maximum at B point or D point. Okay, so don't be so sure of this. Just because it is happening in the first case doesn't mean. I'll try to get one example in which it doesn't happen so that you can actually relate with this. Okay, so this is how you are supposed to solve the optimization problem. How? First of all, get the constraints in the mathematical form. Write down the objective function that you need to maximize, minimize. Okay, draw the straight lines and do the shading of each of the straight line using test point. And 99% time you will be using test point as 0, 0. Always put the value of x and y as 0, 0. Can we do it with other point? Yes. Should we do it? No. Unless and until the question specifies you to do it. How does it specify, sir? It depends on the equation. Right now the equation is working, so there is no problem. The moment this method fails, then we will choose another test point. That happens in a very specific case. I'll tell you when that happens. Okay. So I hope it is clear so far. Then after that, get the overall feasible region. The feasible region is the effectively shading of the constraints of both the inequalities. 2 or 3, any number of inequalities can be there. Get the corner points, get the value of z for each corner point, and then see if it is asking for maximum or minimum. Okay. All right, that's your first question. That's pretty much, I think, summarizes how you have to do this. I'll take one more example. All right. Solve the linear programming graphically. So we are doing graphically, but not with a proper graph as such. And if it comes from objective point of view, of course, you were supposed to solve in a rough manner. The constraints are already created. Z, they have given you 4x plus y. Okay, the constraints they have mentioned like this: x greater than equal to 0, y greater than equal to 0. 99% this will be the constraint. Why? Because we are doing an optimization of physical quantities. Physical quantities cannot be negative. So basically we have two equations. This means first quadrant, and these are the two equations. So again, I need to do a graph. Let's write down the first equation: x plus y, instead of less than equal to 50, let's turn down equal to 50 and create those points x, y. X, y. Put the value of x as 0, you get y as 50. Put the value of y as 0, you get the value of x as 50. Do you need another point? Yes, you can use, but as long as you are getting the 2 points correct, won't make a difference. So 50-50. Okay, let's write down 10, 20, 30, 40, 50. This is 1 point. 10, 20, 30, 40, 50. Okay. So first equation, we'll draw it with the red color. Okay. So again, you can see that the XY plane is divided in two parts, one above the line, one below the line. Now we need to decide which area will be shaded. For that, we'll take again the equation x plus y is less than equal to 50. We'll choose the test point 0, 0. 0, 0 is always less than 50. Yes, true. True means that we will shade towards the test point. That means towards the origin. Towards origin. That means this shading will happen like this. Okay, I'm not pointing this because pretty much I'm sure that the feasible region will come in this section. So just to give you the idea, okay, this is towards the origin to show you. Second equation is 3x plus y less than, forget about the less than inequality. Let's write down the equation x, y. Put x as 0, you'll get y as 90. Oh my god. Y as 0, you get x as 30. 30 is okay. 30, 9, 20, 30. 30 is here. 90, I'll again have to extend this. Always y is getting extended. फिफ्टी तो यहाँ तक हो गया था ना 10 20 30 40 50 हाँ 50 60 70 80 60 70 80 90. This is what these 2 points. All right, we got the 2 points. Let's create the straight line. Green color. All right, 30 50 50 90. Yep. Let's check. This is also less than given, no? So 3x plus y less than equal to 90. Put down 0 0 as a test point. Less than equal to 90. 0 plus 0 is less than 90. True. Again, shading again is towards origin. So that means for this region also we'll shade it like this. So you can see that the feasible region again will be below this red line, below the green line, and restricted to the first quadrant only. So this would be the feasible region. And now again we have the corner points A, B, C, D. So again you can see A, B available, C we have to find, and I told you how to find that. You solve the two equations, red equation and the green equation. That means the x plus y equal to 50 and 3x plus y equal to 90. You solve those two equations. I'm solving it here only. Let's solve it here. X plus y to get C equal to 60. 3x plus y equal to 90. Subtract these equations. Y cancels. Minus 2x is equal to minus 30. X is coming out to be 15. Again, this time it is not looking like it is coming out to be 15. We are drawing freehand, so error can happen. That's not the issue. Okay. That's why. No. It was 50. 50, 50. This should be 40. This should be 20. Again, very close. But again, I will recommend you to solve this. Pretty much from this, I'm guessing 10, 20, 30. It should be 30, which it will be. If you put the value of x as 20 in the first equation, you'll get y as 30. So C point is 20, 30. Okay. Also from the graph, it was looking like this, but not be too sure about this. If you want to guess this, take risk on your part. I've given you the proper way. Now, corner points. Corner points. A, B, C, D. A is 0, 0. B is 30, 0. C we calculated 20, 30. D is, this point is D. So 0, 50 basically. 0, 50. Okay. These are the corner points. Net Z function, the objective function, that was 4x plus y. Okay. 4x plus y. Let's get the value of that. If we put 0, 0 here, so we'll get the value 0. If we put 30, so this comes out to be 120. If we put 50, T point I'm talking about, if we put 50, we'll get only 50 here. If we put 20, 30, so 4 into 20 plus 30 is equal to 80 plus 310. Look at that. The maxima didn't occur at the C point. This is the thing I was talking about. The maximum occurred at B point. So again, I told you, it's not necessary that always the point of intersection will be the point of maximum or minimum. If it would have been that simple, why bother with this? Always solve the equations. Whatever the point you're getting, that has to be maximum or minimum. Okay. So again, so this time the optimum solution is x equal to 20, y is equal to 30. Of course, there will be representing some physical quantity. Right now, it is not mentioned here. And the maximum value, sorry, my bad. X is 30. B was the point, no? B was the point. X is 30, y is 0. Okay. Fine. All right. All right. I think that pretty much summarizes. That pretty much summarizes this. We'll have one more lecture in which I'll explain a few more examples and I'll explain the specific case of unbounded region, because right now what you are getting as this region is bounded. That means it is fixed. It's not an infinite area. Okay, so that means it is bounded. What happens in the case of unbounded? Does it really affect our answer? And about that test point, I told you that 99% of time 0, 0 will work, but I'll talk about that 1% where it fails and what do you have to do in that point. We'll discuss that in the next class. That's it from my part. See you in the next class. Good day, everyone. Bye.